If you've been following current developments in space science or staying updated with cosmic breakthroughs, you've likely encountered discussions about the transformative contributions of the James Webb Space Telescope, JWST. Among its most notable accomplishments to date is the remarkable new image it delivered of Neptune, the distant, icy blue planet that orbits near the outskirts of our solar system. When NASA released this unprecedentedly clear image of Neptune in September of the previous year, it generated a wave of excitement throughout the global scientific community and among astronomy enthusiasts everywhere. This unveiling was particularly noteworthy because it represented the most high-definition view of Neptune in over 30 years. For the first time in decades, scientists were granted access to visuals that revealed features of the planet which had long remained hidden. Sitting at a staggering distance of billions of kilometers from our home planet, Neptune has always presented unique challenges for observation due to its remote location and harsh conditions. Yet, with JWST's superior resolution and infrared imaging capabilities, a fresh window has opened into this elusive world's secrets. To understand why Neptune's new visual record is so groundbreaking, it's helpful to revisit the planet's status within our cosmic neighborhood. Neptune is recognized as the eighth planet from the Sun and is currently the outermost confirmed planet in the solar system, a distinction it inherited after Pluto was reclassified as a dwarf planet in 2006. Measuring by diameter, Neptune is the fourth largest, but by mass, it stands third, outweighing its near-twin Uranus. Its density also makes it the heaviest of the outer planetary giants, with a mass roughly 17 times greater than that of Earth. Unlike the more massive gas giants Jupiter and Saturn, Neptune falls into the category of ice giants. This designation stems from its unique composition, which includes substantial amounts of hydrogen and helium, intermingled with heavier substances such as methane, ammonia, and water. These components contribute to a layered and volatile atmosphere, where the frigid outer clouds conceal a core that may contain scorching, high-pressure oceans rich in exotic ices. Neptune's path around the Sun is lengthy, taking nearly 165 Earth years to complete a single orbit while maintaining an average distance of 4.5 billion kilometers. What adds to Neptune's fascinating profile is the story of its discovery. Unlike most other planets that were located through direct visual observation, Neptune was initially found through mathematical prediction. In the 19th century, discrepancies in Uranus' orbital path led British mathematician John Couch Adams and French astronomer Urbain Le Verrier to independently propose that another unseen body was exerting gravitational influence. Their calculations prompted German astronomer Johann Galle to train his telescope toward the predicted location in 1846, successfully confirming the presence of Neptune. This marked the first planetary discovery driven by theoretical mathematics rather than direct sight. The planet's vivid azure appearance has long captivated observers. This rich coloration stems from methane in the upper atmosphere, which absorbs red light and reflects blue wavelengths, giving Neptune its distinctive look. The planet's name, drawn from the Roman god of the sea, was chosen to reflect this deep, oceanic hue. Despite its aesthetic charm, Neptune has remained relatively underexplored. Observational data gathered over the years has documented fleeting yet intense weather systems on the planet, including massive storms and supersonic winds that appear and vanish with little warning. The only spacecraft to have ever visited Neptune up close was Voyager 2, which performed a flyby in 1989. Launched over a decade earlier, this historic encounter provided the most detailed data on the planet at the time. Voyager 2 revealed Neptune's violent atmospheric dynamics, including storms and winds traveling at speeds up to 2,100 kilometers per hour, some of the fastest wind speeds in our solar system. Its findings were revolutionary, and the imagery it collected served as the definitive reference for over 30 years. Even the Hubble Space Telescope, with all its capabilities, struggled to provide visuals as clear. That all changed in September 2022 when JWST used its near-infrared camera, IRCam, to capture a hauntingly detailed image of Neptune. Unlike the iconic deep blue portrayal, the planet appeared almost black in this new infrared depiction. The reason lies in methane's properties. It absorbs infrared and red wavelengths, causing the planet to look dark and eerie in this spectrum. Yet, against this dark backdrop, JWST highlighted bright regions across Neptune's disk. These luminous areas are actually methane ice clouds high in Neptune's atmosphere. These clouds reflect sunlight effectively and appear as white, gleaming streaks against the infrared darkness. The extraordinary level of detail in JWST's image allows researchers to monitor these clouds' movement and gain a better understanding of Neptune's complex atmospheric behavior. Among the most thrilling aspects of this observation is the highly detailed imaging of Neptune's rings. Though much fainter than Saturn's, Neptune's rings were first spotted during Voyager 2's mission, yet they have remained difficult to observe with clarity. JWST changed that. Its high-resolution infrared view captured Neptune's rings in unprecedented detail, showcasing their composition and structure. Scientists can now study these delicate features to investigate how they formed, how they persist, and what they reveal about the planet's evolution. Another notable feature captured in JWST's image is a sharp, luminous line encircling Neptune's equator. Experts believe this could mark an area of intense atmospheric circulation, a visual manifestation of the planet's extreme wind systems. JWST also caught a vortex near the southern pole and cloud bands at higher latitudes, giving a comprehensive view of Neptune's dynamic weather zones and storm-forming processes. The new data collected by JWST is dramatically expanding what we know about Neptune. Its ability to peer into the planet's atmosphere enables astronomers to dissect the layers of gas, trace its chemical makeup, and understand how cloud structures develop and move over time. These findings are also reigniting interest in Neptune's ring system, which may carry important clues about the planet's past and the surrounding space environment. While other planetary giants such as Jupiter and Saturn have been subjects of detailed missions, like the Galileo spacecraft around Jupiter or the Cassini probe's in-depth study of Saturn, Neptune has largely been left out of such focused attention. No mission has ever been launched specifically to orbit or land on Neptune. Our only close-range data is still from that brief 1989 Voyager 2 flyby. As a result, the planet remains shrouded in mystery. However, the revelations brought forth by JWST are changing that. Its images and readings are not just reigniting scientific curiosity, they're prompting serious discussions about the possibility of sending a dedicated spacecraft to study Neptune. Many planetary scientists argue that such a mission could completely transform our knowledge of ice giants, planetary system formation, and the dynamics of the outer solar system. A mission like this, potentially equipped to orbit Neptune, study its magnetic field, analyze its weather systems, and perhaps even deploy a descent probe, would fill a major gap in our planetary understanding. Neptune's atmosphere contains the most powerful winds in the solar system, and its internal structure remains unknown. Learning more about its layers could tell us how planets form not just in our system, but throughout the galaxy. Adding another layer of intrigue is Neptune's largest moon, Triton. This remarkable satellite orbits the planet in the opposite direction of Neptune's rotation, strongly suggesting it was captured from another region, possibly the Kuiper Belt, rather than forming alongside Neptune. This retrograde orbit and other characteristics make Triton one of the most unusual moons in the solar system. Triton is also one of the few moons known to be geologically active. Voyager 2 observed nitrogen geysers erupting from its surface, evidence of cryovolcanism, where icy materials rather than molten rock are expelled. These findings imply that Triton retains internal heat and might even harbor a subsurface ocean, placing it on the short list of extraterrestrial bodies with potential habitability. Its surface is smooth and relatively unmarked by craters, hinting at recent geological resurfacing. The moon's thin nitrogen-rich atmosphere also displays signs of seasonal activity, possibly driven by solar radiation and orbital positioning. These properties make Triton an ideal candidate for a future mission. Scientists speculate that radar or thermal instruments could detect signs of an ocean beneath its crust, a discovery with enormous implications for the search for life beyond Earth. Triton's arrival into Neptune's orbit is believed to have dramatically altered the natural configuration of the planet's original moon system. Unlike most major moons in the solar system, Triton follows a retrograde orbit, meaning it moves in the opposite direction of Neptune's rotation. This unusual motion strongly indicates that Triton was not formed alongside Neptune, but rather was captured later, most likely from the Kuiper Belt, a distant region filled with icy bodies and dwarf planets beyond Neptune. Its massive size and backward motion would have exerted tremendous gravitational forces on any pre-existing moons orbiting Neptune at the time of its capture. Astronomers theorize that this gravitational interference destabilized the orbits of Neptune's earlier satellites. Some of these original moons may have collided with each other or even with Triton itself, while others were likely flung out of Neptune's gravitational influence altogether. This violent restructuring would have left Neptune's satellite system in disarray, forcing a complete reshuffling of its orbital architecture. Today, Neptune is known to possess 14 confirmed moons, but many of them display highly irregular characteristics. These include eccentric orbits that are not circular, unusual inclinations that differ greatly from Neptune's equator, and varying distances from the planet. Such features provide strong evidence that the system underwent a chaotic period in its history, supporting the theory that Triton's capture played a central role in disrupting the original moon configuration. In particular, the peculiar orbit of Nereid, one of Neptune's largest irregular moons, exemplifies this past turmoil. Its extremely elliptical path suggests it may be a surviving remnant from the primordial moon system that existed before Triton's arrival. Collectively, these irregularities offer compelling clues into the dynamic and sometimes violent interactions that have shaped Neptune's current collection of moons. One moon of particular interest is Nereid, whose highly eccentric orbit causes it to swing wildly in distance from Neptune during its rotation. This irregular path further supports the theory that Neptune's satellite system was violently rearranged during or after Triton's capture. Despite these compelling findings, our understanding of Neptune and its moons remains limited. However, thanks to JWST, the fog surrounding this distant world is slowly beginning to lift. Each image and set of data unveils new aspects of Neptune's intricate atmosphere, ring system, and satellites. It is increasingly clear that Neptune is not just a cold, remote sphere on the solar system's edge. It is a vibrant, ever-changing world teeming with energy and complexity. To truly unlock Neptune's mysteries, though, scientists agree that we need more than telescopic observations. A future mission, equipped with orbiters, atmospheric probes, and landers, would allow for real-time data collection on Neptune's internal structure, storm mechanisms, ring dynamics, and moon system. A detailed exploration could finally resolve long-standing questions and potentially raise new ones about planetary science and the conditions for life in extreme environments. In the meantime, the James Webb Space Telescope continues to serve as our best window into this icy frontier. As it captures Neptune's storms, rings, and moons with astonishing clarity, it's also reigniting public fascination with the outer planets. These discoveries are reshaping our understanding of how planets evolve, how weather systems operate in extreme conditions, and what roles ice giants may play in planetary system formation. Ultimately, Neptune is proving to be much more than a distant, mysterious orb. It may represent a key piece in the larger puzzle of our solar system's origin and evolution. And if Triton indeed hides a subsurface ocean, Neptune's realm might even hold the ingredients for life. As research continues and technology advances, the call to send a dedicated mission to Neptune grows louder. With each new revelation from JWST, we move closer to realizing that mission, one that could change our view of the solar system forever. Neptune, once relegated to the shadows, is stepping into the spotlight, promising to reveal insights that extend far beyond its icy orbit.